Okay, so we've been talking about finding the relative max and the relative min, and we've been using the first derivative to figure out where it's increasing and where it's decreasing in the first derivative test to determine whether it's a maximum or whether it's a minimum. Well, there's another test that we can use, and it's called the second derivative test. So let's see what it says. It says suppose that a function f is twice differentiable at the point x naught. If f prime of x naught equals 0, right, so that means that we've got a stationary critical point at x naught, right, and that f double prime of x naught is greater than 0, right, so when we evaluate the second derivative at x naught, we get a positive value. So if that's the case, then f has a relative minimum at x naught. Right, so think of what we've got. Look over here at this picture that we've got. That's this case over here. Let's see. So, why isn't that picking up? Okay, here we go. Hello. So here's our stationary point, right? So, as you can see, we've got a horizontal tangent line. Right, that's basically telling us it's a stationary point. Right, the first derivative is equal to 0. And the second derivative is greater than 0, which means it's concave up. Right, so what happens? Just like the other one, I draw a quick picture when I'm doing these. It means that at that critical point, you must have a minimum because your curve is bending up. It hits that point and then it bends up. Okay, so that's the first part of it. You can probably guess from the diagram what's going to happen next. If f prime of x naught is equal to 0, right, again it's a stationary point, and f double prime of x naught is less than 0, right, so when we evaluate it in the second derivative, it's negative, right, then f has a relative maximum at x naught, right, so again, here's the case. We've got a stationary critical point right here, right? So the first derivative is equal to 0, you get a horizontal tangent line. But the second derivative is negative. It means that your function is concave down at that point, right? And if it's concave down, it means it's bending downward like that. It means you must have a relative max, right? All right, so you get a relative max if you've got a stationary critical point. So make note of that. This can only be used for stationary points. Right? They can't be used for non-differentiable critical points. So, and the other thing to note for this is that we're not doing a sine graph like before. We're just plugging the critical point right into the second derivative, and the sign of the value of the second derivative at that point will tell us whether it's going to be a relative max or a relative min. And then finally C, if you do the second derivative test and the first derivative at x naught is equal to 0 and the second derivative at x naught is equal to 0, then the test is inconclusive. All right. F may have a relative min, may have a relative max, or maybe neither at that point. So there's not enough to tell the tale here for this. Okay. So for this, I guess there's two things basically we're doing, right? Find stationary critical points. Right, basically by setting the first derivative equal to 0, those values that make the first derivative equal to 0. And then 2, evaluate the stationary critical points. In the second derivative, right? And the sign of the second derivative is what's going to tell us if it's a relative max or if it's a relative min. Alright, so let's see if we can't tackle a problem for this.